All right, so I'm just gonna show like a quick video explaining explaining this big equation that can be used to solve any to model the general equation for any linear recurrences. So before doing this, you should find all the roots of the characteristic polynomial, and after that, you would obtain the general solution from this formula, and then you can solve for each of the constant terms. So this is just equation that can model it. Obviously, you can do it uh, by just like without this formula, but this formula I think it's a good like structure that you can use if you don't have the process memorized. Um, so yeah, so you have a of n is equal to this outer sum. This outer sum basically accounts for all the multiplicity groups, and so you can see that it says that there's z distinct roots, meaning that because each multiplicity group has the same root, right? So if you have distinct roots, then that accounts for all the multiplicity groups that are possible in the list of roots of the list of characteristic roots. So you're going from group 1, group 2, group 3, up until the zth group. Because there are z distinct roots. So you would naturally have z multiplicity groups. And so that outer sum goes through iterates through every single multiplicity group, and each multiplicity group has m of x amount of um m of x amount of terms. So uh say you had like 1 comma 1 comma 2 comma 2 comma 2 and then 4. If this is your list of characteristic roots, then you know that within this group of twos you have multiplicity of 3. Um this has multiplicity of 1. This has multiplicity of 2. And you can see like the multiplicity accounts for how many terms there are. So if we iterate from 0 to multiplicity -1, then we're basically accounting for all the terms. Like say you go from 0 to m equals to 2 for this group for ones. You'll go from 0 to 1. So if you go from 0 to 1 inclusive, then you would go through 0 and 1, and that's 2 terms. And so that counts for both the terms. Why we're doing this is because when we're modeling this part, you see that you have a x comma k. That's the constant coefficient, and so that's basically the a and b that we use for the other problem. And we're gonna solve those. We can solve those using initial conditions that are given, and we're gonna like create system of equations. Um, So then you have the next thing is n to the power of k. N to the power of k is the coefficient, is another like coefficient of the root function that you can add to the function to make sure that the functions are linearly independent. So remember like we had like a 3 to the power of n, comma n 3 to the power of n. Adding the n, there's basically like a invisible n to the power of 0 here, and adding the n will make sure that they're linearly independent. And so to make sure that they are linearly independent, we have the n to the power of k, starting from k is equal to 0, to make sure that you start at 3 to the power of n to make sure that like n to the power of 0 accounts for that one-dimensional solution space. And so you're counting for the right for the right solution space per multiplicity group. And so yeah, you just start with 0. Okay. So you have that n to the power of k term to make sure that they are linearly independent for every single term in the general solution. Um, general solution. One. And then the last term is the r of x to the power of n, and you know that and also x is just the multiplicity group number. So we can assign each multiplicity group a number from 1 to z, which is the distinct roots, the amount of distinct roots, or the amount of multiplicity groups. So so say r of x to the power of n, you basically have, and that would represent the 3 to the power of n in the other case. In the other example. But in this example, if we have these roots, then let's assign this group as group 1. This as group 2, group 3. And so let's take the iteration of x equals 0, is equal to 0 of this. So if you're computing a double sum, then you can take the sum of the outer of one iteration of the outer of the outer sum first. So you have x equals to 1, you evaluate that first. And also z is 3 in this case because there's only 3 distinct numbers for the roots. There's 3 distinct roots, so this would be 3 in this case. And so we're iterating from 1. We have 1, 2, 3. So we're doing 3 times. But we're taking the first one first, so we're using group 1 first. It doesn't matter which order you do it, but we're assigning this as group 1, so we're gonna do this first. Where you have 2 ones, multiplicity of 2. So m of x is equal to 2 because and x is 1, right? So you have m of 1, which basically denotes the multiplicity of the first group. We already said it's equal to 2 because there's 2 ones. And then you subtract by 1, so you're computing the sum from k of 0 to 1, because m1 minus 2 m1 minus 1 is equal to 1 because m1 is equal to 2. You're basically doing 2 minus 1. So you're going from 1 to 2, and notice that this accounts for 2 terms from k is equal to 0 and 1. So we're iterating between those two of 1 comma k, because x is equal to 1, and then n power of k, and then r of x, r of 1, n. And we also know that r of 1 is equal to 1, right? Because the r of x denotes the roots, distinct roots rx. This is equal to r of 2, equal to r of 1, equal to r of 3. And so this can be rewritten as just 1 to the power of n. So you have this for the first sum, for the first group. And to evaluate this, you just plug in 0 and 1, so you get a of 1 comma 0, n to the power of 0, 1 to the power of n, plus a of 1, 1, times n to the power of 1, 1 to the power of n. And so it's also equal to a of 1 comma 0, 1 to the power of n, plus a of 1 comma 1, and 1 to the power of n. You could simplify the 1 to the power of n as 1, but just to showcase that this this is the function of 1 to the power of n. All right, so that's the outer sum for x equals to 1, accounting for group 1. And we can just do the same thing for group 2, which x equals 2, multiplicity m of 2 is equal to 3, as we said here. So we have, like right here, we have m equals to 3 because there's 3 2's. So we basically have the sum of k equals to 0 to 2 because multiplicity of 2 minus 1, multiplicity of the second group is equal to 3, and you do 3 minus 1 is equal to 2. You have a of the second group, comma k. Times n power of k, r of 2, which is also just equal to, we know that the second root, the distinct root is equal to 2. So you have 2 to the power of n. And we can evaluate this by plugging in k equals to 0, 1, and 2. And so we have the sum 2 comma 0 n 0 to the power of n plus a of 2 comma 1 n to the power of 1 to the power of n plus a of 2 to the power of n. And note that the a's are all just coefficients. So you would have to solve for those by plugging in initial conditions. And then we would do the same thing for that's for group 2. And group 3 would have a multiplicity of 1. So 1 minus 1 is equal to 0, right? Because you're doing mx minus 1, right? And in this case, you're doing m3 minus 1, which we know that m3 is equal to 1. Because the multiplicity of that is equal to 1, there's only 1 4. So you're taking k equals 0 to 0 of a of 3 comma k. And to graph k, you know that r of x is equal to 4. So 4 to graph n. This is also equal to just plug in k equals to 0 because that's the only term that you're iterating from. Because the highest index that you're iterating to is 0 and it's inclusive. So you're only doing this from 0 to 0. So you have a of 3 comma 0 and to power 0. 4 to power n. And so after doing all of this, you can combine them all and find the final equation to be the final general solution equation, which you would also you would still have to solve for the individual coefficients of A. Um, but this formula gives you the general solution form. So you finally get so you just add all of them together. So the first one was a of 1 comma 0, 1 to the power of n plus a comma 1 comma 1 and 1 and 1 to the power of n plus um a of 2 comma 0 of 2 to the power of n because n to the power of 0 is 1 plus a of 2 comma 1 times n times 2 to the power of n plus a times um 2 comma 2 times n squared of 2 to the power of n. And then you're adding the third multiplicity group, and that's just, oh, yeah, I didn't finish this. For so a of 3 comma 0 times 4 to the power of n. And so this will be your general solution form, and you should get some initial conditions to solve for the individual a1 comma 0, a11, a2 0, blah blah blah. And after you find those coefficients, you would have the particular solution, which gives you the explicit formula for whatever condition I give you. So that's the recurrence that you can. This is the formula that you can use for the recurrence to solve for the explicit formula. But make sure that you find the characteristic roots first, make a list, and then make the list of multiplicity groups, organize it, uh, list out their multiplicities, and then after that you can start plugging in into the equation. But the equation is just like an organized form that you can use. You don't have to like always use it or like memorize it. But definitely know how to use each group. Um, like make sure to understand this concept of linear independence, where if you have a certain multiplicity group, you would have to add a multiple of n each time to account for like the proper solution space per uh, multiplicity group. Since if you have the same multiplicity group, that accounts for the same one-dimensional solution space. And yeah, so just add an n every single time, and you should be good. Yeah, and that's all.